All right, so 4.6, modeling with exponential functions. So this is a very practical section that we're going to look at. So most of these, pretty much all word problems, but fairly, I don't know if I'd say simple formulas, but fairly, we're going to kind of see the same formula over and over again with little variations depending on the context of the problem. So the first one we're going to look at is the doubling formula. So if we have an initial population in 0 and naught, and the doubling time is A, and A can be measured in whatever time unit, so you can see minutes, hours, days, years, whatever. Then the size of the population at time t is given by this formula. So you have the initial amount times 2 raised to t over whatever the doubling time is. And this works for it doesn't have to be doubling time. It could work like if you have tripling time or half time, whatever number you're looking at, you would put there. But doubling time is the one we're mostly going to work with for now, at least. So let's look at this first example. Under ideal conditions, bacteria doubles every 3 hours. Initially, there are 1,000 bacteria. So we're going to find a model for the bacteria population. So this will just be N of T equals 1,000 times 2 to the T over 3, because we're doubling every 3 hours. Then how many bacteria are in the colony after 15 hours? So we are just, that's not 0.3, that was just a straight mark. How many bacteria are in the colony after 15 hours? So this will be N of 15, so we get 1,000 times 2 to the 15 over 3. Put that in the calculator, and we should get 3,200. And then after how many hours will the bacteria count reach 100,000? So now we're going to solve for t. So we're going to say 100,000 equal to the formula, and then solve for t. So this is where the things that we learned in the last section come into play. So if you recall from the last section, we need to isolate the exponential part of this. And so we'll do that by dividing both sides by 1,000. And we get 100 equals 2 to the t over 3. And then we can take the log. You can take any log that you want. You can do ln on both sides if you want, but I think it's easiest if you just do log base 2, and then that will cancel out that. So if we do log base 2 of 100 equals log base 2 of 2 to the t over 3, then the log base 2 and the 2 cancel, and we end up with log base 2 of 100 equals t over 3. Then we can multiply both sides by 3, and we get t is 3 log base 2 of 100, and that should come out to about 19.9. So after 19.9 hours, you go from 1,000 bacteria to 100,000 bacteria. All right. Next one. So now you can also convert this, and we'll see how to convert this in a minute. You can convert doubling time to just continuous growth. So whenever we have this formula with the E, that's looking at a continuous growth. So we're not just saying at time 0 it's this much, and then at 3 hours later or 3 years later, whatever it is, it doubles this way. And you can do this with the last one also, but this is another way to look at growth. And this is more of a continuous type of growth. So we have initial bacteria count 500, later makes a sample count and finds a relative growth rate is 40% per hour. Find the function that models the bacteria after the hours. Sorry, I got my pages a little bit out of order there. So this will be N of T. equals. Now, in this case, it doesn't say, are we looking at the doubling period or anything like that? Well, actually, if it has this percent, that tells you they're kind of thinking in terms of exponential. So N naught would be 500. That's the initial amount. E to the, now we're growing, so it's positive 0.40 or 0.4 T. And then we can plug in, what's the estimated count after 10 hours? So we can plug in 10. So N of 10 would be 500 E to the 0.4, 40 times 10. And it should come out to about 27,300. Then after how many hours will the bacteria reach 80,000? So we're going to set the function equal to 80,000 and solve for T. So we'll divide both sides by 500. And we get 160 equals E to the 0.40 T. Then we can take the ln of both sides. And the ln and the E will cancel out, so we just have the 0.40 T and then divide by the 0.40. And so we get T is 12.7. All right, so you kind of notice a pattern here. I mean, most of the problems are kind of going through this same sequence of questions. And once you set a formula, it's really nothing too complex as long as you as long as you practice what we did in 4.5, where we were solving these equations. That may be the trickiest part, depending on how well you're doing at those. All right, for radioactive substance with a mass m naught and half-life h, the amount remaining at time t is modeled by this function. And it's important h and t are measured in the same time units. So you always want to make sure you do that. Now notice they use the 2, but they have the negative exponent. So you could write this as m naught times 1/2 to the t over h, make the exponent positive, but this is the same thing. And it's kind of easier to remember. The negative indicates decay. We'll see that in part B as well. So find a function. So we have this polonium-210 half-life of 140 days. Have a sample with a mass of 300 milligrams. Find a function. So this will be m of t equals 300 times 2 to the negative t over the half-life, which is 140. Then part B, now we're going to change this to the exponential formula. And so you can actually, you could write a formula for this, but I tend to think that it's better to be able to do this without memorizing formula if possible. And so it's not too difficult. So we're essentially solving this equation. And so we're just kind of letting t equal 1 and then setting the exponential parts of the two formulas equal to each other. So let's take the log of both sides. So we have, or ln of both sides. So we have ln of 2 to the negative 1/40th equals negative r. And then you can bring this down, so or put it in that way. It doesn't matter, but you should get r equals negative 0.0002000495. And then so that makes our formula m of t equals the initial now is 300 e to the negative 0.00495 b. So that is our formula. So the formula for this that I was referring to is r equals ln of 1/2 over whatever the half-life is. Or sorry, yeah, that would work. Or maybe it's ln of 2. Should be ln of 2 over, no, that would work. ln of 1/2, sorry, I didn't work this out beforehand. ln of 1/2 over h, that would work. And that would give you a negative r. So r is supposed to be negative because we're decaying. So yeah, that would work. So ln of 1/2 is negative, and then divided by the positive half-life, which would be 140 in this case. All right, so now find the mass remaining after 1 year. So now this is where the time units come in. So we have 1 year, but we're talking t is measured in days. So we actually need to write this as 365 days. So m of 365, not m of 1. And so that's 300 e to the negative 0.00495 times 365. And we should get 49.3 for that. And the last one, kind of the same thing we've been doing. And in this one, you can use either formula. And actually, you could use either formula here, because these two formulas are equivalent. So it doesn't really matter which one you use. So find, or how long will it take to decay to 200 milligrams? So we're going to say 200 equals 300 e to the negative 0.0045 t. We'll divide by 300. So we get 2/3 equals e to the negative 0.00495 t. Take the ln of both sides. So ln of 2/3 equals negative 0.00495 t, and then we'll divide. And we should get t equals 81.9. So this, if you don't, most people don't like word problems. This section is all word problems, but you don't really have to read. You don't have to read anything too carefully. Most of these, you're kind of looking for keywords like half-life, and then you'll see another number usually. And so we have the units. That's going to be the initial amount. So you don't really have to. Yeah, they're not long word problems. You don't have to read them too closely. You're just kind of looking for a couple of things in them. Formulas are mostly similar, a couple of either using a 2 or an e. And then we kind of are following the same, write the function, how much is left after so much time, and then how long will it take to get to a certain level. Kind of do it very, very repetitious at least. But if you have any questions, you can email me, and I'll help you the best I can.